one of the important thing why we actually what we discussed is like why we need to perform model analysis. The important thing here is uh, we need to perform model analysis in order to extract frequencies of the component of assembly. So each frequency will have different mode shape. Okay. So one is we need to extract the frequency. Model analysis is performed to extract frequency and mode shape. Okay. So the great question comes: why we need to extract frequency? The main reason is we need to check the resonance, so operating frequency. So one of the important thing is what will happen if it matches. So as we studied in our previous schools, because of resonance, there will be catastrophic failure. So it is for us to have a good margin from the rating frequencies. So to understand more on this, let us look into some case study. So before going to case study, so model analysis is performed in extract frequency and motion. Apart from this, we sometimes in stress analysis we also perform model analysis to check the model, FE model, whether the built FE model is built properly or not. So, that is the one. All the red lines shows which are present. This is the branch implications. These are the branch implications. So the case study is perform model analysis on this case and check the resonance. Okay. So what we have taken is like we have taken a shell model instead of building 3D model. We have taken shell model and we used shell elements to build the model, FE model. So we have meshed with the shell elements and we have assigned real constants. You see here, these are the real constants assignment. So this is shell elements with the. So we perform the model analysis of this component by constraining this case at this end, and we perform the analysis, and we observe there is a opening here. Okay, and we got frequency very low frequency 0.9. It's almost 0. So one of the reason is there is a mesh discontinuity, and it is clearly visible. Okay. So this is how it is very useful model analysis to check the mesh discontinuity, any issues with the finite element model. So then we went back and fixed these things, and we performed the analysis. So what we observed, like the geometry is like cylinder diameter is 30 inch, and case wall thickness, that is the thickness of this case is 0.08 inch, and we extracted 5 frequencies, and we got 137 fundamental frequencies. Secondary frequency is also same, and we got 219 as a third frequency, and 321 210 frequency same again. So what we have done is we constrain this case and we perform the model, and we got 137 frequencies. So our main objective is to So our main objective is to perform model analysis and extract fundamental theory. Second one is take the margin as the operating speed. Frequency margin. Operating speed is 1250 RPM. Okay. So this is the first mode. It's 137 Hz. Frequency here. This is the third mode, first mode, and second mode. This is the first mode. This is the second mode, same 130 Hz. And this is the third mode, 219. And this is the fourth mode. We are at 320. This is another mode. And this is the fifth mode. Again, it's a 320. So we extracted total 5 modes, and now the important thing is we need to check the frequency margin, the operating speed. So our operating speed is at 1250 RPM, and we need to convert into frequency. So 2,560. That will be around. So around 131 Hz. So we need to check the margin. So the margin here we need to see 20% margin. So on the first fundamental frequency it should be 20% from this 131 Hz. So 20 is 131 plus 20. It should be 157. But we are at 137. So the current mode geometry, it is having fundamental frequency of 137. Okay. So but our requirement is 157 to have a 20% margin. Then it requires a redesign. So this is a summary table. Requires a redesign of the frequency margin of 20%. We have put together 5 modes here. So our natural frequency first frequency is 137, and our operating frequency is 131, and we are at 5%. So but we need to have minimum 20%. So to get 20%, we need to go for redesign. So one other thing. So yesterday what we discussed is we have 2 things. Model analysis can be in model analysis these frequencies can be changed. Frequency equation is given by x equals to 1 by 2 pi over k by a. So we can increase how our we need to go for redesign to increase the frequency. To increase the frequency, we have 2 options. One is increase phase or decrease mass. Increase phase or decrease mass. So now suppose here we didn't try concrete material. I kept in this case study we kept material content. Material constant. We are not changing material. So only option is now we need to increase Ka. Okay. Effectively, we need to change the design such a way that if you change the design, it will affect both thickness and mass. Okay. So we need to ensure that we should have effectively increase the stiffness mass the mass. The effect of changing the design should have more effective mass stiffness rather than mass. So the increase in stiffness should be more than increase in the mass. So that's why we need to change the design. So one option we can increase thickness is changing the cylindrical case. So option is this diameter is fixed. We cannot change the diameter. Only thing is we can change the case wall thickness. So I perform some analysis by changing the case wall thickness. So I have taken a shell model. Okay. Here in shell model it is very easy to run several design iterations. The reason is mesh is there and we assign real constant. The thickness is assigned as a real constant. So we won't disturb mesh, but we will be playing with the real constant. So I did several iterations by changing real constants. The current thickness is 0.085 inch. This is baseline 0.085. So the case wall thickness is 0.085 inch. So we get this is the baseline. We got 137. Now our option is to increase the thickness. So to increase the thickness, we need to see whether thickness will be increased, frequency will be increased or not. So we went with instead of 0.085, we went with 0.1 inch. And good thing is stiffness is increased 149 volts. Then we went further and increased another 10% in case wall thickness, and it is 155. So we went for another 5% increase in the case thickness, and the stiffness is 159. Frequency is 159, and finally we went with 0.125 and it is 165 first. And now let us conclude. Let us look into the summary table. So we are having 0.5 inch case wall thickness, and fundamental frequency is 137 for baseline design. And we are at 5%. So when we try to increase the case wall thickness to 0.1 inch, there is an increase in the fundamental frequency, and it is up to 14%. So we went further with the design iteration 2. It's 0.110, and the frequency is 55, and we are still at 18%. Then we further increased to 115, and it is 21%. So finally, last iteration with 125.125 inch, and it is 26%. So overall, if you see here, we have 5 design iterations, out of which first baseline and first design iterations are not meeting, and the second one is marginally it is meeting 18%, but our requirement is 20%. So we can take the design iteration 3 as a final geometry, and we conclude that design iteration. Sorry, here typo is here. Design iteration 3 is the optimum design, which means frequency criteria 20%. That is the case wall thickness 0.115. Okay. So this is the overall case study. This is how model analysis is required for stress analysis area in order to meet the frequency criteria. So if you see, like yesterday, we also discussed about the effect of the geometry, effect of parameters on moisture, frequency, so there are 2 things. One is the stiffness and boundary condition. Let us see which one is affecting. So stiffness. Now we have studied a case study now by changing the case wall thickness. So stiffness can be increased in 2 ways. Stiffness can be increased in 2 ways. One is increasing in material property or geometry change. So, for example, yesterday we always discussed about cross section A, length is L, and E is L. So, thickness is nothing but AE by L. So, if you want to increase the stiffness, we always look for increase in area. We should not add. We should not add increase the length. So we should not increase the length. Okay? So always we should add increase the area. So stiffness can be increased either by changing the material properties or changing the geometry. So when you try to increase the stiffness, frequency will be increased. Okay. So motion, any change in the motion? So right now, like in this study, you see here. So this is the baseline. Okay, we changed the geometry, and if you see the mode shapes, all mode shapes looks alike. So from this, it is understandable that increasing the thickness won't have any effect. No effect on mode shape. Okay. So whether it is boundary condition, frequency will it will affect, and the mode shape will also affect. So yesterday we saw there are two things. One is cantilever beam, and another is simply supported. So just we are changing the boundary conditions here. The complete behavior of the beam will be changing. Okay. So this is just summary, overall summary. So if you increase the stiffness, overall most stress will be changed. But if you change the concentrations, most stress will change, frequency will change. If you change the stiffness, frequency will be changed. Okay. So any questions on model analysis? Buckling analysis today, and tomorrow I would like to cancel tomorrow's session. Thursday I will take a final session where I will be discussing few case studies. So we have been discussing about static analysis for quite a long time. Okay. So what exactly is static analysis? So static analysis is basically classified as like whenever you perform any static analysis, we always ignore the dynamic effects of a system. Okay. Suppose if there is a dynamic loads acting on the system, the response of the system will be completely dynamic. Okay. So whereas what we assume that in static analysis, the system is always in stable conditions after load application, and then we'll perform the analysis. So no dynamic effects considered in the static analysis. Static analysis, so basically we can do both linear and non-linear. Okay, linear is F equals to Ku. F is so where F equals to Ku, where K is depends upon overall geometry, okay, on the displacements. So we can what we can do with the steady loads? What are type of loads we can apply? We can apply gravity loads, rotational velocities, that is inertia body when a rotor is subjected to uniform angular velocity, so, or when bar is subjected to vertical gravity load, okay, or you can apply temperature, thermal gradients, okay. So and you can apply pressures, you can apply point loads. So all those types of loads can be applied in static analysis. So in linear condition, we assume that there won't be change in the stiffness matrix of the overall geometry. And in nonlinear static analysis, what we can see here is stiffness is a function of displacements. So stiffness keep on updating. So as load is applied, stiffness of the geometry keep on changing, as well as same is the case with the forces. So that is the reason we'll call it as a nonlinear. So basically, in nonlinear, as we discussed earlier, it is a completely iterative process, and it will take time because what it will do is it will take, instead of solving it in one time step, it will take multiple time steps, and it will try to converge the solution. So, and it is a completely iterative process, and it will take time. So compared to static analysis, nonlinear static analysis is completely time consuming, okay. So here three types of non-linearities in the system, in this nonlinear analysis. One is material. Generally whatever we do, whenever load application is behind plastic region, then we need to go for elastoplastic analysis. So here generally we perform plastic analysis, that is when load is applied behind elastic region. So if our load application causes stresses below the yield, okay, then it's a linear analysis. Elastic, we can say elastic. We perform only elastic analysis. Suppose our because of load application stresses may exceed beyond yield, then we need to go for elastoplastic analysis. So that this will be the material nonlinearity. So here in elastic condition, we give only Young's model, density, and Poisson ratio. Whereas in plastic condition, elastoplastic, we give Young's model, density, Poisson ratio, and we also need to give this information. We have two ways of giving this information, that is bilinear or multilinear. Okay, bilinear and multilinear. So these things we discussed in our nonlinear analysis chapter. So you can refer those things. So in elastic we need to give only Young's modulus, density and Poisson's ratio. In elastoplastic we need to give elastic, density, Poisson's ratio, as well as the plastic curve. So this is elastic, and this plastic curve also we need to give, and this plastic curve can be given in two ways, like either bilinear or multilinear. So this is on material nonlinearity, and geometric nonlinearity. We have large displacements. Okay, whenever a structure undergoes very large displacements, that need to be carried. That will be under geometric nonlinearity. Okay, so because the loading behavior, everything will changes. The stiffness of the component will be changing. So the stiffness of a component, when it is this way, is different. When it is this way, it is different. Okay, so there is a large displacement is there. So whenever there is a large displacement, the stiffness of the component will be changed. So these things need to be incorporated in our things. So that can be taken care by nonlinear analysis. So we need to specify geometric nonlinearity, material nonlinearity. If you give material plastics, it depends upon load application. It will automatically take it as a nonlinearity. Whereas in geometric nonlinearity, we need to clearly specify the geometric nonlinearity. So it all depends upon type of load and type of structure. We need to analyze. So we need to assess whether it will come under large displacement or small displacement. And then boundary. So the boundary is basically when you try to model interface components. If you see, there are two flanges here. These two flanges are need to be interface at this interface location. This we can achieve either giving some couplings or constraints, or we can use contacts. So whenever there is a contact, whenever you define a contact, there will be nonlinearity coming into picture because of stiffness, adjoining material stiffness, everything. So there will be nonlinearity coming into picture. So contacts will also come under nonlinearity. So there will be change in the boundary conditions because of the load application and the contact definitions. Most of the chapters we studied basically more are relevant to static analysis. So types of loads, boundary conditions, most of the things will come under static analysis. So buckling analysis is one of the important aspect in stress analysis. It is very important to understand basically the for any given geometry. So if you take any geometry, okay, these two together will have some ultimate capacity loading, ultimate buckling load capacity. So for any geometry is designed for operating load. Say so it is very much necessary to see that whether that applied operating load is well above the ultimate buckling load capability. Okay, so so suppose if a component generally buckling is happens only when component is subjected to compressing load. So basically the buckling definition is change in geometry of structure under compression that results in ability to resist the loads. Okay, so basically it is purely because of compressive load the buckling phenomena can happen. So buckling is a phenomena that can occur for structures under compressive loads. The equilibrium state becomes unstable due to large deformation of the structure. So this may be deformed or inelasticity of structural materials. Okay, so either way it can happen, whether either it is due to large deformation or inelasticity of the structure's material. So if you see here, there are three cases here. So the applied load is less than critical buckling load. In this case, P is the applied load, P critical is the buckling critical load. So applied load is well below the critical load. So there is no buckling happening. Okay. So in the second stage, the applied load is almost equal to critical load. And if you see the dotted line here, if you see the dotted line here, that means the structure starts buckling, started buckling. So if you try to increase further this loading more than the critical load, so it's already buckled. This structure is already buckled. That means it exceeded the, it went to the plastic zone, and this structure no longer take any extra additional loads. So so buckling analysis is basically will be done in order to evaluate the ultimate buckling load capacity of the geometry. Okay. So and then we need to check the margin against the applied load. So always applied load should be much less than the P. Okay. So applied load should be always less than the buckling load. So this is the trademark rule, and it should have very good margin. So some people will take 100 margin is 2 or 30 1.3. So we'll see some examples on this margin also. Okay. So whenever structure subjects to compressive forces, it can undergo buckling, bifurcation of equilibrium from deformation. So there will be disturbance to the equilibrium, and also failure due to instability of the equilibrium due to large deformations. So there are two ways. One is like this is related to equilibrium of loads. Whenever there is a buckling will happen. Otherwise, there will be due to large deformation, the material will go in elasticity. Okay. So elastic instability occurs for the beams, columns, frames subjected to gravity and lateral loads. Elastic instability can occur to all members and frames. This is general information about elastic instability. So whenever compressive forces happens, there are two ways. One is buckling, another one is instability of equilibrium due to large deformations. So if you see here, like we might have studied about buckling loads in our strength of materials. So there are various conditions here. One end fixed, pinned, fixed, hinged, all those things. There are 5 conditions over here. So all are given by Euler buckling. So Euler buckling is given by this equation, K into pi square A by L square, where K is given for each condition. So for this condition, equation 1, condition 1 will give maximum buckling load. So it can withstand maximum buckling loads. Okay. So 4 times of so this is the most worst condition. It's like cantilever type of thing, but cantilever type with axial loading, it will give worst one end fixed and other end free. This will give worst buckling load. Similarly, there are other conditions as well. So in stress analysis, basically, all these things are evaluated based on Euler equations. So in stress analysis, we can do in 2 ways. One is linear buckling analysis, and another one is non-linear buckling analysis. So in linear buckling analysis, it uses Euler value buckling analysis. So the Euler and buckling analysis is whatever we studied in our strength of materials. So same formulas it is used to calculate the buckling loads. So some information about Euler eigenvalue buckling analysis. This is also known as Euler buckling analysis. This analysis generally predicts theoretical buckling strength of a ideal elastic structure. So that means it assumes that structure is very ideal and it will give the theoretical buckling strength. So it computes structural eigenvalues for a given system and loading and constraints. Generally, for a given geometry and given loads and constraints, it will calculate the buckling eigenvalues. So what are these eigenvalues? So generally, when you perform any buckling analysis, it will give eigenvalues. E1. So what it says is E1 is nothing but buckling load is given by P buckling equals to E1 into P applied. So basically this one is ratio of buckling load by applied load. So generally E1 is calculated in our stress analysis, in buckling analysis. Buckling loads for several configurations are readily available from tabulated solutions. So if you take simple configurations like this type of configurations, you can directly go through hand calculations. No need to do stress analysis. But if our geometry is so complicated, then we need to go for a buckling analysis in finite element method. Okay. So if it is geometry is very simple, like simple rectangular cross section. So if you see in this equation, so only thing it is very tough is I value and L value. So if you know the end conditions, you can get L value. But I is moment of inertia. This moment of inertia can be if it is a geometry is very simple, we can go for hand calculations. Suppose our cross section will keep on changing throughout the length, then it is very difficult to evaluate. In that conditions, definitely we need to go for stress analysis or buckling analysis using finite element method. So it predicts the expected buckling loads. So whatever predictions given by eigenvalue buckling analysis, generally it will or predicts, and it is not recommended for to get accurate buckling prediction. Okay. So if it is or predicts buckling load means then the buckling load is not accurate and it's not to exact to real world buckling predictions. So in this analysis, the magnitude of resultant buckling load factor must be greater than the applied load factor. Okay. So applied load factor is P applied by P applied. That is one. So definitely E1 should be greater than 1. Eigenvalue should be greater than 1. Definitely. So that is one thing, and another type of buckling is nonlinear buckling analysis. As it indicates non-linearity,
So there are two ways of buckling nonlinearity can be taken care. Uh, large deflection. Okay. Nonlinear buckling analysis is more accurate than eigenvalue analysis. So generally, if you see this curve, okay, this is where it should stop. But our eigenvalue buckling, it will go up to this point. So there is a lot of uncertainty in this range, okay, and it generally it over predicts compared to nonlinear buckling analysis. So generally, like nonlinear buckling analysis, at least it will give very accurate buckling load capability compared to eigenvalue buckling analysis. So nonlinear more accurate than eigenvalue analysis because it implies nonlinear large diffraction static analysis to predict buckling loads. Generally, it employs nonlinearity. It will take one is large diffraction, second one is elastoplastic. That means material nonlinearity. Material nonlinearity. Okay. So it will account both large diffraction and material nonlinearity. So because of nonlinearity is accounted here, it predicts accurate buckling load. So for this type of analysis, note that small off-axis loads are necessary to initiate desired buckling analysis. That means like when you try to solve any model with this type of loading, there should be always small offload. Okay, small offload so that it will try to deflect in this way, and the buckling phenomena can be initiated. So this is a nonlinear buckling analysis. Okay, so and more information on nonlinear buckling analysis. I would like to give. So I want to apply load here and that here. Okay, and this is our time of number of substeps 0 to 1 time. Now, what we need to do in nonlinear buckling analysis, we need to give very tiny substeps. Okay, so each substep it will try to solve the analysis, get the convergence result. Okay, so it will solve until a point where divergence will happen. Why the divergence will happen is like there will be change in the large deflection. There will be very high deflections. That means even small load application also there will be very high deflections happen. That's where instability will happen. Okay, so it will stop at that location. Okay, so that load will be our buckling load. So that will check with the operating load. That will give buckling load back. So basically, we'll divide into number of substeps and we'll perform the analysis. So each substeps it will solve and it will give convergent results, and it will stop at a particular location where there will be instability. That means even small applied load also, very negligible load also, it will have a tremendous deflection. That means the structure won't have any load bearing capacity. It loses all the load bearing capacity and it is completely unstable. So at that condition, we'll extract that load. That load we'll take it as a buckling load capability, and we'll try to divide with the operating load, and we'll get the buckling load factor. So this is how we evaluate in nonlinear buckling analysis. So actually this nonlinear buckling analysis is a very advanced activity. So you can restrict yourself to eigenvalue buckling analysis. It is more or less similar to model analysis. So I'll try to put together some case study in next session, and we can discuss on that. And coming to calculating the buckling criteria. So basically, generally we may use either 2 or 1.3 times. Okay, so generally we can go with the 2 times, or we can go for directly check the margin. Okay, so here what we'll do is we'll calculate buckling load. Okay, so buckling equals to eigenvalue factor into P operating. Okay, so this is our buckling load. Definitely this should be greater than 1. Then we'll calculate margin of safety. That is nothing but P buckling by P operating minus nothing but EVF P operating. So margin of safety is nothing but EVF minus. So this should be greater than 0 generally. So it all depends upon how much we want to have this margin. So this whatever the values we have given, this we have put together instead of some people they will put 1.3, some people they will put 2. It all depends upon the requirement given by the customers. Okay. In practice, we'll go with 1.3. So I'll try to refer some of the books. In theory, what is the value we need to consider here. Generally, you can calculate margin of safety like this. Okay, no need to apply any factors over here. Here we put a factor 2, so that is not required here in practice in general. So that completes all the analysis in chapter 5, and I'll run through some of the interesting case studies in next session. So one case study I want to run on static analysis. I'll list out what are the case studies I'll be running in next session Thursday. One on buckling. Static analysis. Other one is any other critical. So maybe I'll try to get